Hello everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying Continuity Lecture 2. This is QOD 17, take the screenshot. Now today we'll be studying regions of discontinuity. So there will be three regions for discontinuity. Let's look at the first one. The first one says limit doesn't exist. So we know that LHL should be equals to RHL should be equals to f of A, where A is the point which we are concerned with for the continuity check. So basically if this is happening, and also these should be finite. If this is happening, then function is continuous. Now, if limit is not existing, so it can be two cases. The first one is the limit is infinity. So basically, let's take this point 0. Let's take this point x equals to 0. We are talking about over here. Now, even though the function might be defined, let's say f of 0 equals to 4, but we can see that LHL is infinity and RHL is infinity, right? So basically, it does not exist. Now, since limits are not existing in that case, we can say that the function is discontinuous. Now, the second case is let's say function is like this. Now, again, over here, we can see that limits are existing, but both limits are different. So basically, LHL is not equals to RHL. So both individual limits are existing for x equals to 0. So in totality, limit doesn't exist because they both are not equal. LHL is not equals to RHL, and thus the function is not continuous. Now let's look at the second reason. Limit exists, but function is not defined. Now let's take one more example. An open circle over here. Now we can clearly see that LHL and RHL. This is LHL. This is RHL. They both are same. They both are close to this one. But we have an open circle over here. The function is not defined over here. You can take one more example like this one. So let's say like this one. So we have an open circle over here, but we can say that LHL and RHL are existing at this point. Let's see, this point is A. So over here, function is not defined. So when function is not defined, we cannot compare it with the limits value, right? So in that case, function is discontinuous. Now the third reason is limit exists, function is also defined, but they both are not equal. So let's take similar kind of example. Again, we have an open circle over here, but a closed circle over here. So basically function is defined over here. Let's say this value is 4 and this value is 3. So we know that LHL equals to RHL equals to 3 over here, but f of 0 equals to 4. So they both are not equal. In that case, the function is not continuous again. So these are the three reasons for which, because of which functions can be discontinuous. Now, these are the few important pointers which you need to remember and understand. So basically, the first point says all polynomial functions and rational functions are continuous, except for the points where denominator becomes 0. So basically, all polynomial functions are continuous. So we know that x square plus 1, x square minus 1, x minus 1, x cube plus 1, any polynomial function is continuous. But in case of rational functions, let's say we have a rational function like this, x cube minus 1 divided by x minus 1. In this case, we know that this becomes 0 at x equals to 1. This function becomes not defined. So basically, a denominator becomes 0, and this function becomes non-defined. Now over here, we cannot say that this function is continuous at this point, right? So basically, at all those points except the points where denominator becomes 0. Now the second point says exponential, log functions, trigonometric, inverse trigonometric, and modulus functions are continuous in their domain. So basically, let's take an example of tan. We know that this is pi by 2. This is minus pi by 2. Now function of tan looks like this. So basically at pi by 2, it's not defined. So basically just at the left hand side of the pi by 2, it reaches infinity, and over here just at the right side of minus pi by 2, it reaches minus infinity. So at exact minus pi by 2 and pi by 2, it is not defined. So basically, what is the domain of tan function? Tan function r minus, in let's say we are talking about over here. So here domain is minus pi by 2, say pi by 2, right? So these endpoints are not included. So if we're talking about endpoints, it's actually discontinuous over there, but in its domain, it's actually continuous. So similar thing is there for logarithmic functions, trigonometric functions, inverse trigonometric functions, and modulus functions. So whatever the domain part is there, these functions are continuous. Now the third point is always check for discontinuity in case you see GIF and fraction part functions. So let's say take an example, fx equals to GIF of x divided by x. Now we know that GIF function is always discontinuous at integers individually. So basically we'll have to check if this entire function GIF of x divided by x is actually discontinuous or continuous at integer points or not. So whenever, just make it a habit that whenever you see these functions GIF and fraction part, just make sure that you are checking at the critical points. Now let's solve these examples. Find the points of discontinuity of the following functions. So the first function is fx equals to this one. So we know that this is a rational function involving modulus as well. So what I'll do, I know that mod x square equals to x square and vice versa. So I'll write it like this. Mod x square minus 3 mod x plus 2. Now I can see that this gets factorized mod x minus 1 mod x minus 2, right? Now I know that when mod x equals to 1 or mod x equals to 2, the denominator part becomes 0. So basically this function becomes not defined in these cases. So basically if I open this mod x, then I'll get x equals to plus minus 1 and x equals to plus minus 2. So at all these 4 points, I can safely say that this function is not defined. So at all these points, this function is discontinuous. So we studied that rational functions are continuous everywhere except for the points where denominator becomes 0. So we have to find the points where denominator actually became 0. Now let's look at the second function. So we have fx equals to 1 upon 1 minus e raised power x minus 1 divided by x minus 2. Now we have two cases over here. The first one is considering the entire rational function. So over here, if 1 equals to e raised power x minus 1 divided by x minus 2, if this happens, in that case, the function is not defined. So we'll find a point over here. And the second one is x minus 1 divided by x minus 2. So we can clearly see that x equals to 2 is 1 point where this function is not defined. So if this function is not defined, then this entire function is also not defined because we cannot calculate the value of this e raised power x minus 1 divided by x minus 2 over here, right? So we got 1 point from here. We'll get second point from here. So this becomes 1 only when this becomes 0. The power becomes 0. That happens at x equals to 1. So basically x equals to 1 and x equals to 2. These both are the points where the function is not defined, or basically function is discontinuous. Now let's talk about types of discontinuities. So there are two types of discontinuities, removable and non-removable. So these are being described based on the existence of limits. So in case the limit is existing, in that case, it's removable. And the second case is if limit is not existing, basically maybe the LHL is not equals to RHL, maybe it's infinite, maybe it's oscillating. In that case, it's non-removable. So we have two further divisions of removable type of discontinuity. The first one is missing point and the second one is isolated point. Let's take few examples. Let's talk about a missing point first. Now let's take an example. Let's say fx equals to x squared by x. Now we know that the function is not defined at x equals to 0. It's not defined over here, right? So we can clearly say that this function is discontinuous at x equals to 0. So this function can be written as fx equals to x when x is not equals to 0 and not defined when x equals to 0. Graph looks like this. Then open circle over here. So at x equals to 0, the value is not defined over here, right? So that's why the name missing point. The point is actually missing over here. So that's why it's not continuous. Now the second version is, let's take similar example. We do have an open circle over here. This is x-axis, this is y-axis, but the point is defined over here. Let's say this value is 5. So the function is defined like fx equals to y equals to x when x not equals to 0 and x equals to y equals to 5 when x equals to 0. Now the function is defined at x equals to 0, but it's different than LHL and RHL. So basically LHL equals to RHL equals to 0, but that is not equals to f of 0, sorry, right? So that is 5. So it's not equals to 0, right? So in that case, we know that the point is not missing, but it's isolated over here. It's somewhere else. So this is the second type of discontinuity, which is isolated type. Now let's talk about non-removable. The first one is finite type. So that is very simple. So this can be the simplest example for describing this kind of discontinuity. So over here, LHL is not equals to RHL. You can clearly see that. Let's say this value is 4 and this value is 5. So you can clearly see that LHL is not equals to RHL and hence limits are finite, but they're not equal and hence discontinuous. Now let's talk about infinite type. The simplest example can be this one. Now you can clearly see that at x equals to 0, LHL is not defined. Similarly, RHL is also not defined because they both are actually infinite. And when the limit is infinite, we say that they are not defined. So hence the name infinite non-removable discontinuity, right? Very simple example. Now let's talk about oscillatory. Sorry. So the standard example for this one is fx equals to sine of 1 by x. Now let's take an example. Let's say x equals to 10 is for minus 10 and x equals to 10 is for minus 11. Both are close to 0, right? Both are close to 0. Both are approaching 0. But we never know that. We cannot know that what kind of value sine would take if this is the value and if this is the value. So my point is, let's say what I do, x equals to 10 is power minus 10 and let's say add 1. If I do this, I take these two denominators. So I am actually moving my x by a nanoscale, but still the angles are fluctuating by a large value. And that's why at every point, the value is fluctuating. So the graph would look like this one. So it would be something of this sort. And then it will go on smoothen out. Similarly on over here. So that's how the graph would look like. So this looks like very big distance, but it's very small. It must be of the order of 10 is per minus 10 or something like that, right? So in such small scenario, that kind of graph would look like. So that's why the name oscillatory. So we cannot have a stable value over here. So today's lecture was till here only, and tomorrow we'll be continuing with the lecture number 3 of continuity, and with that we'll completely wrap up the continuity series. And tomorrow we'll be doing theorems on continuity and few examples. So let's meet tomorrow. Thanks for watching.